Here is another standard application that we're going to see both in the way I'm going to present it to you, as well as in some of its variations, and that's population growth. You've probably seen already in high school. And the idea is the following: if you have a biological population, you know it's going to reproduce, and rabbits are going to reproduce more than others. Okay, well, maybe not as much as bacteria, but you get the point. Okay? Now, one of the things that you may want to do is you may want to have an idea of how big is the population as time goes by, right? So we want to have an idea of how many rabbits there is going to be 3 years down the road, 5 years down the road, or something like this. Well, and of course we're not going to talk about rabbits only. If we make certain basic assumptions, then we'll be able to come up with a fairly simple differential equation. The assumptions are the following. First of all, we're going to assume that the reproduction rate is going to be constant, so it's not going to change over time, and homogeneous, meaning that it's going to be the same for all subsets of the population itself. So we're not going to have pockets of highly reproducing elements and pockets of people who are watching TV all the time. The other assumption is that there is a limitless supply of food. So in other words, there is not going to be a problem with lack of food and all the problems that entails. And similarly, we're going to assume that there is no predators that are going to affect the population. These last two assumptions actually can be relaxed a little bit, as long as the supply of food is in fact sufficient for the population we're dealing with, and the predators, if there are any, have an effect which is pretty constant, again, doesn't change over time. Well, if all of this is true, then we can assume that the rate at which the population is changing is going to be proportional to the population itself. So in other words, the percentage or the proportional rate, how fast the population grows with respect to how big the population is going to be constant. So if that is the case, then here we have another differential equation, right? And this is a special one. Again, the goal is to find out what the population is as a function of time. And this is something which is called the exponential model, or the exponential differential equation. Now you may wonder why it's called exponential, since there are no exponentials in that equation. Well, you'll have to wait until next class to find out.